Hello and welcome to this video. In this video, we're going to look at all of the interactions that we looked at in the particle interactions video. We're now going to put a diagram to them. So we're going to use a technique made by Richard Feynman that is Feynman diagrams. And this is just maybe a pictorial way of imagining what's happening, but we're also going to throw in the idea of having different exchange particles in the mix as well. So if we remember back, we looked at alpha decay, we looked at beta minus decay, we looked at beta plus decay, and we also looked at electron capture. Okay, now all of these things can be shown using a Feynman diagram. Okay, so Feynman did a lot of work in what we would call quantum electrodynamics, or QED, which sounds really fancy. But essentially what he was doing is he made these diagrams so that he could do calculations based off these diagrams that allowed him to find out a lot of stuff about how things interacted with each other. For this video, we're not going to worry about the Feynman diagram of alpha decay, because alpha decay is more of a whole nucleus type of decay. So it's not a particle that's decaying so much as a whole nucleus. So we don't have to worry about alpha decay when we're looking at Feynman diagrams. But in the other three, we always have maybe a proton decaying into a neutron, or a neutron decaying into a proton, or a proton combining with an electron, or something like that. Okay, so these are the three that we definitely have to know. I'm going to do a fourth one that's just going to be electron repulsion, just to show you something different, so it just gives you a better idea of how we use Feynman diagrams as a whole. So the first thing we have to look at are what are some conventions of the Feynman diagrams. If you wanted to Google a Feynman diagram, you'll probably find that different people have different conventions, especially as you get higher levels. You will see that a lot of the Feynman diagrams will get a lot more complicated, or they'll have arrows pointing in what you would assume would be the wrong direction. But it's just because the conventions of the diagrams change as you do different things with them. For the purpose of A level, so I would just, fair warning, if you wanted to go online and search for these things, make sure you're looking at some sort of A-level revision website to stop yourself from getting confused. Our conventions are that our arrows point as if they're going into the reaction or coming out of the reaction. Interaction, I should say. Point into interaction or out of interaction. So obviously the things that are decaying, so for example the proton that's decaying is going to have an arrow going into it, because that's what's starting off the decay, and then all of the products that are formed will come out of it, and that will be the going out of the decay. So that's where we'll have arrows coming in and out of this. We're also gonna use this squiggly line for exchange particles. Okay, so we're gonna have this to represent all exchange particles, and we'll always label it with maybe like a W minus, maybe a W plus, maybe a photon. It depends on what interaction we're looking at. Okay, so these are the two main conventions. You can get a third that says that gradually the x-axis would be the arrow of time, but I personally wouldn't go with that because it doesn't fit with everything that we're doing. Maybe in some of these the y-axis would be time, but I'm not going to put that as a convention because it can change depending on how you draw the diagram, and you can always rotate about different places, so it's kind of gets a bit tricky around when we're looking at time axes and stuff like that. So let's just look at each of these individually. So let's first go with beta decay. Okay, so if you remember back to beta minus decay, Beta minus decay was when we had a neutron decaying into a proton plus an electron and an anti-electron neutrino. Now, the way we're going to draw these, each of these particles is going to be represented by a solid line. Okay, so we're going to say, let's have the particle of a neutron going into the reaction. It's going to have some sort of vertex there. And that's because this is the interaction here. This is where we're going to form our exchange particle. Okay, now we'll label it to show which exchange particle we have at the end, but for now we just want to show what's coming in and out. So this neutron forms a proton. So a proton is going to come off of there, and on the other side we're also forming an electron and an anti-electron neutrino. Okay, now this is a decay, which means it's a weak interaction. Okay, which means we have to have W minus, W plus, or Z naught. And the way we're going to choose which one is we look at what's the charge on the electron, and this is E minus, so this is going to be W minus. Okay, the reason is because just these W plus, minus, and Z naught are there just to conserve energy, momentum, and charge, or to transfer energy, momentum, and charge. So because this charge is negative, this charge has to be negative just to balance them out. I want to go a little bit further than this as well, because we also said that we could write this as a down to an up plus an electron plus an anti-electron neutrino. And so if we make a bit of room for that, we can have the exact same thing, but we have some spectators. So the down goes in to the vertice or the vertex, the up comes out, we get the same exchange particle produced. It's still going to be W minus, and we still get an electron and anti-electron neutrino emitted. You might sometimes see they'll have these things here that you'll see aren't actually involved in the interaction, but they are to the side of this, and this is just the rest of the and then there we go. This is just the rest of the quarks in this. So this is the neutron and this is the proton up here. And the reason we have to include these is because, like I said in the quark video, we can never get a quark by itself. It has to be part of a system, so it has to be a baryon or a meson. So even though these up and down quarks aren't actually in this interaction, they're not changing anything. They're still there, so we still have to include them in that. Okay, but this would be the beta decay Feynman diagram. Let's do the opposite of that, and let's look at beta plus decay. And in beta plus decay, we just had a proton go into a neutron plus an E plus an electron neutrino. And so we start with a proton going in. We form our exchange particle. We have E plus, and the electron neutrino coming out. We also have the neutron coming out over here. This is a positive electron here, so we're going to have a W plus. So this is beta decay. We can again look at it as if it was the quark identity instead, so up to down like this, and then we're going to have an up coming in. We form our exchange particle that has an E plus and a electron neutrino coming out of it. It's still going to have a W plus exchange particle, and that's this up is forming a down, and then down here we still have these two coming across, and because this down here is the proton, we need to have another up, so that up doesn't change, and we need to have a down, and that down doesn't change. So you can see we're changing from a proton to a neutron because this up is changing into this down. And those are the two beta decay Feynman diagrams. So now the other one that we said we would go through is the electron capture. So let's look at electron capture. So we said what electron capture is when a proton basically absorbs an electron from the innermost energy level, forming a proton and releasing an electron neutrino. So it was proton plus electron goes to neutron plus electron neutrino. And so what we can have here is we can say that we have a proton and an electron coming into the reaction. So let me draw it like this. So I have a proton coming in. There's some interaction going on, so we have some exchange particle. But over here, we have the electron coming into the reaction. And then going out over here, the electron becomes so the lepton sticks with the lepton, and over here, the baryon sticks with the baryon. Okay, now in the middle, this is going to be W minus because the electron is minus. And this is your electron capture Feynman diagram. The way I've drawn this is very much following the idea that this is time going upwards, right? Because we have the proton and the electron both coming in because they start the reaction, then after the interaction, which is what this W minus represents, we have a neutron and an electron neutrino going out. So that's after the time has surpassed, and then we get the products of this reaction or interaction. Okay, there isn't a secondary like quark thing for this, although you could, but it's not really asked too often. So what I want to do is, all of these have been weak interactions. Let me show you an example of something that might be an electromagnetic interaction, and that's why we have this electron repulsion. Okay, so electron repulsion is literally just an electron repelling off another electron. I could have done proton repulsion. I could have even done proton-electron attraction because you have two different things. But what's going to happen is if I've got an electron coming in, so this is my electron here, I've got some interaction with this electron, and I know afterwards, because they're just repelling, they're just going to bounce off in opposite directions. And these things, everything here is charged. So this is a electromagnetic interaction. We'll see in the exchange when we're looking at conserving quantum values how we decide whether it's a weak interaction, strong interaction, or any of those. In this case, it's quite easy because we just basically going to say all of these are charged, so it has to be the things that are affected by things that have charged particles, which is the electromagnetic force. This electron capture has a neutral thing in here, which means a neutral lepton, so it's not made of quarks, so it can't be the strong force. It's not charged, so it can't be the electromagnetic, and it doesn't have mass. Well, for A level, it doesn't have mass, so it can't be the gravity, and so we're left with the only other thing, which is the weak nuclear force, which acts on everything. Okay, hopefully all of these Feynman diagrams make sense. Like I said, if you want to go and find more interactions, feel free. Just make sure that you're looking on the right A-level websites, because when you get to higher levels, this kind of stuff gets a bit trickier because you can have multiple interactions all on one diagram. But for the most part, you will just have to basically memorize these interactions, and they look really impressive to people who don't know what's going on. So thank you for watching.